Okay, for this Unit 6 FRQ, the first one says this gaseous acetaldehyde, and gives a molar mass, undergoes combustion according to the following reaction. So pay attention to this reaction. We're going to use that several times. Notice we need 2 moles of the acetaldehyde. We do this, we're going to get 4 CO2s, 4 H2Os, and we're going to get 5 O2s. If we were to do the reaction, we would have gotten fractions for the oxygen if we use 1 mole of acetaldehyde. So we went back and doubled everything. So 2, 5, 4, and 4. So when 79.62 grams of acetaldehyde is consumed, 4309 kilojoules of energy was released. That's important. And the process takes place in a container against an external pressure of 101.3 kPa, temperature is 25 degrees, and the volume of the container decreases. Okay, so what we have to do, we have to figure out what's the work and what's the change in energy of the system. And so we think about this, well, work, has a formula for that. But the other part is, is it going to be the energy of the system going out or is it going in? So we're saying here, if this energy is released, then that means the system is losing energy as a heat. But the work, the volume is being decreased. If it was expanding, then it would be doing work and reducing the energy. But what's happening here is that because its volume is decreasing, then work is being done on the system, and it's the change in energy is going to go up. So the change in energy is going to go down because of this 4309 kilojoules, but it's going to go up by the work done. So first thing, let's go back and figure out the work. Okay, and work is P delta V. And officially, if we're going to go by signs, it's negative P delta V. Okay, so what's the pressure it's working against? 101.3 kPa. And what's the change in volume? Okay, 66.3 liters. But since it's decreasing, then it started larger, okay, and then it ended up smaller. So it's going to be a small number minus a large number. So that's going to be a negative 66.3 liters. So when we get done putting this in, here it is right here, okay, then we have P delta V, so negative 101.3 kPa, okay, negative 66.3 liters, and we should know that a kPa times a liter is equal to a joule, given right there. So when we get all done, we're going to find out negative, negative. We're going to get positive 67.20 joules. And that's what we were saying. We're saying that the work is done on the system. That's going to increase the internal energy by, in a positive way. So positive. Now notice what we have here is Q is negative, okay, 4309 kilojoules, watch those units. And this is positive, but it's joules. So we have to find the work. So the work we found out that is positive, okay, 6720 joules or 6.72 kilojoules. And then the internal energy is the work and heat, okay, so it's going to go down by, we change this to joules now, 4,309,000 joules instead of kilojoules. And it's going to go back up by 6720 joules. So bottom line is the change in the energy is negative 4,302,000, 4,302,000 joules, or we could say it's negative 4.302 kilojoules. But watch out those units, one's joules, one's kilojoules. Okay, the next one, what's the value of the delta H? Okay, so the delta H for this reaction is the heat divided by the moles. So we have to go back and go back to this fact that we had 79.62 grams, and we know that the molar mass of that, there it is, 44.05. So we have to say 79.62, okay, that's grams of the acetaldehyde divided by 44.05 grams for 1 mole of acetaldehyde. And if we do that, that is where this 1.81 moles of acetaldehyde comes in. So we have the energy, the negative 4309 back to kilojoules, divided by the moles. Okay, then this is per reaction. And so since the reaction is 2 moles of this acetaldehyde for every 1 mole of reaction, then we put in, so for every 1 mole of reaction, there are 2 moles of acetaldehyde. So what do we have? So we have 1.81 moles, 2 moles of acetaldehyde for every 1 mole of reaction. So when we get all done, we have 4,760 kilojoules per mole released, okay, so negative 4760, and that's our number. Now, notice up here it says, let's assume that the work is negligible, okay, and delta H's are usually carried out in systems where the volume cannot change, so that the P delta V work is always 0, okay, so the energy change is the delta H. So Q over N, we get that number there. Okay, for C, using the structure of acetaldehyde and the average bond energies given here, figure out the approximate bond energy for the CO bond. Okay, approximate bond energy of the CO bond. Well, what we know about is we know that we have this equation here, okay, for combustion, and we know the heat of combustion right here, okay, the negative 4760. So we're going to do this whole thing about the bonds that are broken and the bonds that are formed. And as we come on down here, so we have a reaction. We're going to have 2 of these molecules, plus, we said 5 O2s, turns into 4 CO2s and 4 H2Os. And we're laying this all out so you can kind of see what the bonds are. So what's happening? For the whole delta H to happen, then we have to break 1, 2, 3, 4 CH bonds twice. And we're going to break a C, I'll change color, a CC bond, okay, we're going to do that, and it's going to happen twice. And then we have a C double bond O bond, and that's the one that we're interested in, okay, there. And again, that's going to happen twice because we have 2 of those molecules. So there we're breaking, and then we're also breaking up these 5 oxygen molecules, so 5 OO double bonds is going to get broken up. Okay, and then the products, we're not breaking these, we're making these. So what do we have? We have 1, 2 C double bond O bonds, but we're doing that 4 times. So we have 4 times the CO double bond, 2. And here at H2Os, we're going to break up 2 OH bonds, okay, but that's going to happen 4 times. So 2 OH bonds 4 times. So if we can kind of put that out in words, where we're going to break all these bonds, we're going to break those bonds, okay, but we're going to make these bonds and make these bonds. Well, bond energies are the energies involved in breaking up the bonds. So we're going to use these numbers as is for all these guys, for the reactants, and then when we get to breaking, forming these bonds, then we're going to have to change the sign. So if you follow very carefully, I'm just going to put numbers in. So the negative 4760, that's kilojoules, that is the delta H, and that's from back up here. And now we're going to say, okay, 2 times the 4 times the CH bond, so CH is 413. Okay, this 347 is the CC bond. Okay, and then we're breaking a C double bond O bond, and that's the one we're looking for. So we're calling that delta H, that represents the bond energy of the C double bond O. And all this stuff is happening twice. And then for the ones, we have the the O double bond O, from the oxygen molecules, we have 5 of those. Okay, then for the products, okay, we have the C double bond O, 2 of those for every CO2 molecule, and we're going to make it negative because we are not breaking it, we're making it, and there's 4 times those 2, so 8. And then here we have the H2Os, so the OH bonds, it would be positive 467, but we're using negative 467, change the sign because we're not breaking them, we're making them. So 2 of those for each molecule times 4 molecules. So when we get all that done, we can put it together, it becomes an algebra problem. So we have negative 4760 equals 2737 minus 6 bonds, 6 CO bonds. And this is going to mush that around and find out that the bond energy for any one of those CO bonds is 1250 kilojoules per mole of those bonds. So 1250. So it's a pretty large number, okay, for that C double bond O, but that's not too surprising because that's a strong bond. Okay, letter D. Okay, acetaldehyde is used to form ethane. Use the following reactions to determine the value of the delta S in joules per mole Kelvin for the combustion. So the idea is, again, we have this equation. Okay, actually it's written down here. So we have this equation, and we're kind of using Hess's law, or we're definitely using Hess's law, okay, given these two equations. Now, this is done with S's, and that's work. Hess's law will work for delta H's. It'll work for delta S's. It'll work for delta G's, so if we have that information. So if we can put these two equations together to get this equation, then we can put their delta S's together to get the delta S. And that's what we're doing here. So we say, well, I want to have the acetaldehyde, CH3CHO on the left side, and I need two of those. So here, this molecule, I have it, but it's on the right side. So if I take this number and just, switch my equation around, and that means I'm going to have to change my sign on my delta S. So you can see right down here, we have positive 323.86 instead of negative 3.386. Okay, so that's what happened. And the second one, okay, we can see, well, I want CO2s and H2Os. I do want them on the right. So that part's okay. We don't have to flip the equation. But I need 4 CO2s and 4 H2Os, and this equation has 2 and 2, which means I'm going to have to double my equation, so double this reaction, and therefore I'm going to have to double my entropy change in here. So what we're here is negative 267.68, and you can see what we're going to use down here is double that, negative 535.36. So here's the first equation that's just been turned around. Here's the second equation that's been doubled. And now we can put these two equations together. So everything on the left cancels everything on the right. So those two C2H4s go away. And we have 6 O2s, we have 1 O2. So we get 5 O2s, and everything else stays. And that gets us this equation. 5 O2s, 4 CO2s, 4 H2Os. And we add these two delta S's together, and we get the delta S. So that's how we can get the delta S for this equation. So it's a Hess's law using delta S's instead of delta H's. So the first equation had to be flipped, second equation had to be multiplied by 2. So we changed the sign on the first delta S, and we multiplied by 2 for the second delta S, and added those together. Okay, for E, what is the value of the delta G for the combustion of acetaldehyde? Okay, and is it spontaneous? Okay, well, the spontaneous is going to come back from, what the value of delta G is. So we'll come back to that later. Okay, to get the delta G, well, right back here, we just got finished figuring out, I'll get a new color, we just figured out here the delta S. Okay, so we know our equation, delta G equals delta H minus T delta S. So we got a value for delta S, negative. And back here, we had a value for the delta H. So we know delta H, we know delta S. Be careful, this is in joules, and the other is kilojoules. Okay, and we know that this is at 25 degrees Celsius, which is 298 Kelvin. So delta G equals delta H minus T delta S. We're going to put in delta H, that's from above. Here's the temperature in Kelvin. Here is the negative 211.5 joules per mole Kelvin, and then we're going to do 1,000 joules per kilojoule. Okay, so divide by 1,000 and put all that together, we get negative 4699 kilojoules per mole. Okay, because this is negative, then we know that the reaction is going to be thermodynamically favorable. It's going to be spontaneous because we have a negative delta G. That's all we need to say. Okay, for F, if we're told the delta G formation of CO2 and the delta G of formation of H2O, okay, can we figure out the delta G of formation of CH3CHO? Okay, so back to this equation. Okay, this is the products minus reactants kind of a problem. And the idea is we know this number and we know this number. We're just told that in the problem. Okay, we know this number, the delta G, because we just figured it out in the last problem. And the delta G of formation of oxygen is 0, because, we're talking about formation from its elements. It's already an element, and so its value is 0, kind of like a delta H of formation. So we know everything we need. We're just going to do 4 times this number plus 4 times this number minus 2 times this number, okay, equal, and plus, 5 times 0 is going to equal the delta G of the entire reaction, which we have here. So now it just becomes an algebra problem. And so we can see we have set it up kind of in words to keep things straight. So 4 times the CO2 number plus 4 times the H2 number minus 2 times the acetaldehyde number and 5 times the O2 number, which is 0. And we know what the delta G is. Okay, we had that from the problem right above. So we start putting in all the numbers, and we're just going to solve for 2 times the acetaldehyde and then divide that by 2. And we get an answer here finally of negative 1087 kilojoules per mole for the delta G of formation of acetaldehyde. So it's kind of set it up carefully and then just do the math. Okay, for G, at what temperature is this spontaneous? Okay, so let's, I'm going to get myself a new color. Okay, so what is spontaneous? Way back here, okay, we learned that the delta H of this reaction is negative. So the delta H is negative. Okay, and then down here, where we were doing the S's, okay, here, then we learned that the delta S is negative. So remember we talked about if we have a delta H is negative and a delta S is negative, then that is going to be a temperature dependent reaction. And if it's negative, negative, it will be spontaneous at lower temperatures. It'll be spontaneous at lower temperatures. So we're going to say, okay, where is that cutoff temperature? Well, if it is spontaneous, delta G is negative. If it's not spontaneous, delta G is positive. So what we care about is when is delta G 0? We want to find that value. And then in this case, we're going to say it's going to be spontaneous anything lower than that value. So delta G equals delta H minus T delta S. Okay, except if delta G is 0, okay, then we can substitute, we can turn it around. So T is going to be the delta H over delta S. And again, watch out for your units because G is in kilojoules. Okay, delta S is in joules, so we have to put 1,000 to 1 in there to have them come out the same. And when you do it all correctly, you get 22,500 Kelvin. So it's a very high temperature, but that's the crossover temperature. So anything higher than that would be non-spontaneous. Anything lower than that is going to be spontaneous. So what temperatures is spontaneous? Anything less than 22,500. Okay, number 17. Okay, consider this catalyzed isomerization of cis-2-butene gas to trans-2-butene gas. Okay, and you really don't even really need to understand what this is, but it's not that tough. We've done the carbon compounds, so we have a cis and trans. And going back and forth, we have some data about this. And the data is that the delta H goes from negative 7 to negative 11. So negative 7 to negative 11. So let's think about that for a couple seconds. Okay, let's say that that's negative 7 for our cis. The trans is negative 11. It's even lower. Okay, so it's going to be like an exothermic reaction. And we could figure that out. We could figure out what's the delta H for this reaction. It's the final minus the initial. So negative 11.2 minus negative 7, that's going to give us like a negative 5. Okay, so what's the question? The question is compare the bonds between cis-2-butene and trans-2-butene. Assume that the corresponding bonds between the compounds have the same bond energy except for this C double bond C. Okay, so any other bonds here are going to be exactly the same, but that C double bond C could be different because, you know, these two are on the same side. It's going to be a little bit more repulsion than if they're on opposite sides. So there's going to be a little bit more strain here in that double bond. So you expect it's going to be a little bit different. So the potential energy graph for the C double bond C for each structure is shown below. Figure out which one is which, okay? And the two clues are the, you know, the separation and the energies. Well, here's where the energy comes in. When we're doing a potential energy diagram, okay, delta H's, then, you know, here we say this is negative 7, okay, and this is negative 11. So the key thing is that, you know, this is more, the second one is more negative than the first one. Bond energy is the energy it takes from here. I always think of it up to some arbitrarily place where you're going to break up all the molecules into separate atoms. So this from here up, that's the bond energy. And for here, this up is the bond energy. Okay, so the products have a greater bond energy than the reactants. Okay, the products, in this case, have a greater bond energy overall than the reactants. Now we know from these two structures, the only thing that's different is the C double bond C bond. Everybody else counts the same. So if this is a greater bond energy, that means that this C double C bond must be a greater bond energy than the first one. So if it's a lower energy, it must have a greater bond energy. So if we have a greater bond energy for the trans, that means that this longer one here, this deeper one, okay, this one must be the trans, and the other one must be the cis. So because it's a longer bond energy, it must be the trans. Now, when Mr. Ku says the cis structure has a smaller C-C bond energy because its delta H is more positive and it has a higher potential energy. Okay, so we're saying that he's saying it backwards. I mean, not backwards. He's saying the opposite of what I am. He's saying that this one here has a smaller bond energy because it starts higher. So again, visualizing this helps me. The bond energy is the energy from here up, you know, to separate all the bonds into separate atoms. So if it starts higher, it's got a smaller bond energy. If it's lower, it's got a greater bond energy. Okay, so we're saying that the trans CC bond has the greater bond energy. It's going to be the larger dip, and that's why this one is trans and this one is cis. Okay, for B, find the values of delta G for this reaction. Okay, well, delta G, we can go back to our old standby. Delta G is equal to delta H minus T delta S. Okay, and again, we know that the temperature is 298, 25 degrees. Okay, so if we have delta H and we have delta S, we can find delta G. And we do have delta H and delta S, or we have information so we can find that. So we're going to take the final minus initials, so negative 11 minus negative 7. Okay, and for the delta S, 296 minus 301. And watch out for our units. So here's the delta H. So if we subtract those two, we get negative 4.2 kilojoules. And for the delta S's, if we subtract those two, then we get negative 5 joules. Okay, so again, 296 minus 301. So we get a negative value. And notice this is joules and this is kilojoules. So substitute it in. So we get the negative 4.2 kilojoules per mole minus T 298 minus the, times the delta S, which is negative 0.005 kilojoules. So we have to take into account the fact that this is joules and this is kilojoules. So we divide that by 1,000, 0.005. And so bottom line is we get negative 2.71 kilojoules per mole for the delta G. Okay, and calculate the value of the equilibrium constant. So we have our old equation. And remember, the equation is not given like this. The equation is given where delta G equals blah, blah, blah. So, you know, you might want to make sure you can convert it to this or just memorize this for yourself. And so the KEQ is E to the negative delta G over RT. Okay, so we have to get that, and then we're going to put E to that power. Okay, so now we just substitute in. So we know the delta G. So this is negative 2.71 kilojoules per mole. And we want the negative of that. And this is the point. I like to change this kilojoule into joules. So that's my numerator. My denominator, I have 8.314. And that's joules per mole Kelvin. And that'll be given on the test. And the temperature is 298. Kelvin. So Kelvin and Kelvin, they drop out. Kilojoules and kilojoules, they drop out. Moles and moles, they drop out. And I've got joules on the bottom, I've got joules on the top. So everything cancels out. And when we do this, we get 1.09. And if we take e to the 1.09, okay, because I had negative, negative makes a positive, then we get an answer of 3.0. So it's just a huge plug and chug equation. Watch your units. Okay, again, over and over and over in this test, you got to watch your units because some things are joules and some things are kilojoules. And a lot of you guys don't bother putting in your units, and that is going to totally mess you up. So you got to be really careful with your units on this test and on the AP test. So that gets us to the end of this practice test. Good luck.